Hello students. Given that we have completed the course, I just wanted to uh, give some concluding remarks on how we have progressed over the span of the last 3 months and what all we have learned and what lies next with respect to computer systems. So to begin with what we have learned in the course, so we started with the very basic point on what is computer architecture and where does it fit in our computer science and engineering, right? So where do we come across, and we realize that it's everywhere. Whenever you want to use any sort of hardware, it has some underlying architecture, and this course is specifically about how to understand that. And following that, in the module 0 we got introduced to the basic components of a computer. Then we also looked at some of the great ideas in computer architecture. So even though they are termed as great ideas, we do realize that they are pretty much uh, used in our day-to-day lives also, right? And it just says how effective the simple uh, ideas are when driven by common sense, right? We want to optimize power, latency, area, reliability, and how do we not do it in our day-to-day lives? That's what we adapt in architecture also. And following that, we started understanding how to quantify the performance of a computer, right? We looked at the basic performance equation, what all parameters are involved, and what all how to measure each parameter, and how to interpret the output of such uh, equation, basically the time, and how do we compare two computers by using this performance equation, right? And in module 0 you also had one small assignment on digging uh, the hardware details of your mobile and a laptop, or your personal PC. So this was done basically to give you a feel of all the terms that you are going to learn in the course. I hope now if you look back at this assignment, you will be able to uh, understand almost 70-80% of the terms that you have entered during the assignment. Following module 0, we moved on to module 1, where we looked at the term called instruction set architecture, what it is all about, and what all information is given in ISA, and how the hardware and software are built following an ISA. And we also looked at two predominant ISAs categories, which are RISC and CISC. One is for reduced instructions and other is for complex instructions, and your typical Intel AMD processors will fall under CISC category. Specifically, they are the ISA is called x86 ISA, and RISC ISA are more pertaining to some smaller or simpler systems, but it's now being widely adapted for any generic system also. And we studied the RISC-V ISA because of its increasing relevancy and applicability in the current uh, computing systems design, right? And in module 1 we also had the lab part, where you all had hands-on experience on assembly programming, right? Using the RISC-V ISA, we used Venus Simulator thanks to the developers, and we also had a couple of lab tests to help you understand how well you are able to grasp things. After we understood an ISA, we started diving in closer to the hardware, and we tried to answer a question about how the instructions are executed in the hardware. And accordingly, we got introduced to control path and data path. And The very first implementation that we saw was a single cycle implementation, and with slight modification, how it can be made multi-cycle implementation. But both of these are non-pipelined implementations, and your phase one of the project was implementation of the non-pipelined execution itself, right? Either single cycle or multi-cycle. In the second half of the module, we have looked at a very important concept called pipelining. We started with the very basic idea, then we extended it to the instruction execution, the ideal pipeline, and then we started adding the realistic aspects to it. In the process, we have introduced a lot of small modifications, and we came across an important concept called pipeline hazards and different pipeline hazards and how to handle them, both software and hardware approaches. Following that, we had a couple of discussions on what exceptions are and how to handle exceptions in the pipeline. And then we also had a discussion on how to measure the performance of a computer which has a pipeline implementation in it. When it comes to the lab part, we had the phase two of the project, which was converting the non-pipeline implementation to a pipeline implementation. Basically, it was designed to give you hands-on experience on all the issues that we typically see in a pipeline implementation. So whatever you have read in the theory, you had an opportunity to implement that in your own code, right, in your own processor that you were building for RISC-V ISA. Moving on, in module 3, we were looking at how the instructions and data are stored in the memory and what is an ideal memory, and in the process of answering how we would achieve ideal memory, we looked at memory hierarchy and the concept of locality, both spatial and temporal, and we were looking at few examples on what locality is and how it will help us with a realistic memory. Following that, we looked at the cache organization, cache controllers, and what all design options are available when it comes to associativity, block size, replacement policies, right? Then we looked at the virtual memory, the very basic concept of it, and we looked at the concept of page table, and then a cache for the page table, which was translation, look aside buffers, how they are organized. Then we looked at the implementation aspects of the actual memory or the main memory, where we looked at the DRAM organization and various tasks that the memory controller would need to perform. Moving on, we would have looked at the SSD controller along with the flash organization, but in interest of time, I have not discussed it. The lab part of module 3 was about building the instruction and data cache. Of course, if as a simplistic model, I have asked you not to capture the impact of a cache miss in terms of the performance, because that would need you to implement a lock-based system where the pipeline will explicitly wait for a response from the caches, etc. Right? So even there we can have some simplified models, but again, in interest of time, I just asked you to implement the instruction cache and data cache and understand how the indexing is done, how we identify a hit or a miss, etc. And in module 4, I wanted to discuss, or at least in the past 3 lectures, we discussed how our understanding of the underlying processor can help us to write better programs. Better in the sense they can run faster than those programs which were naively written. I hope all of you would adapt these approaches whenever you are writing programs anywhere. It can be high level or assembly level. At even I know even if you are using tools like MATLAB or any other tools. So keep in mind that at the end of the day, they all will run on some hardware, and whatever you have learned in this course are some of the fundamental topics which will be relevant in any hardware that you run your program on. So I strongly urge all of you to think. Of course, the very first step would be to write the program itself, but then pause for a moment, think about how it would run on the hardware and try to make it better. So the lab assignment that I wanted to give, uh, but I scrapped, was exploring the optimizations that we discussed in module 4 using a tool called CashGrind. Right, it's a very fascinating tool which will give us insight on how the actual cache hierarchy on your laptop or PC is working. Right, if you have interest, just Google for it, and uh, there are a lot of small examples that will that will help you to appreciate the tool, CashGrind tool itself. So that's what we have learned so far in the course. And if you want to know what lies next, the best part about computer architecture is also the challenging part, is that it's a very niche area. It not many people are working on it, but it also says that not many people are qualified to work on it. That's because it is always continuously evolving. It is not something that the hardware we built 20 years back would still work now. We need to come up with newer designs, and those designs are primarily motivated or driven by the next generation products and applications that we want to deploy them for. Also, if we come up with a better hardware, it will also drive the next generation products and applications. So it goes either way. So the consumer is driving the producer, and also producer is driving the consumer. Overall, we would see more faster hardware with much complex applications running on them. And like I said, it's a niche area. The more you learn, the more valuable you will be uh, in the industry. That's primarily because of your knowledge, you will be able to connect the dots well, and to reason out why something is working, why something is not working, and if something is not working, how to improve that. With respect to the courses that will further help you to learn about the computer system stack further, are advanced computer architecture. Then we have embedded systems course, low power design course, memory system design course, and hardware security is one of the hot topics all across. The thefts that are happening, and how, of course, most of the time you will be hearing about the software aspects of it, but even the hardware is prone to some security vulnerabilities. And hardware security is one of the topics which deals and makes your system more robust. We uh, we have another course on compilers, which will help you to understand how the high level language and the ISA, with the help of ISA, will be helping us to come up with more efficient assembly codes. Of course, there are tons of optimizations that the compilers do, right? The end assembly code or the binary code that you will see will not be even understandable also. the flow wise, and it will definitely be an injustice if I will not mention about the operating system itself. That is the main, uh, you can say, face of from the user front. The operating system is the one which wraps up all the complex components and presents a neat interface to the user. Right? You will have courses on operating system and advanced OS. And apart from this, you will have come across a lot of courses on applications, right? The machine learning, uh, primarily. At the end of the day, it's an application, and you do keep in mind that it should run on one hardware or the other, right? There are many courses in the applications, and in typical software development role, you will be working on one application or another, and you'll be refining it further. But there, I would strongly feel that the module 4 will come in handy for you. So with that, I will pause this lecture. I wish you all the best for the upcoming and some examinations. The situation outside is quite bad, so don't venture out. Please take care of yourself and your families. Bye.